Hi, good morning, everyone. Thanks to the organizers for inviting me to this conference, which has a very exciting format. And I look forward to discussion with other conference participants during the live session. So as a way of introduction, my name is Kavilan Moodley, and I'm a professor based at the Astrophysics Research Center at the University of KwaZulu-Natal. This is in sunny Durban on the east coast of South Africa. And just in terms of background, to let you know that there's a growing community of astrophysicists and cosmologists in South Africa, and government has been investing in key facilities such as SALT and Meerkat, with the SKA dish array, to be built here in the Karoo Desert in South Africa. We're also building HIRAX in the Karoo near Meerkat, and we have benefited significantly from the infrastructure that has been established in this area. It's a so-called radio astronomy park. Now, South Africa is well known for its lions and elephants, but you can also come to the Karoo to see hyraxes and meerkats. Right, so in terms of my talk, it'll focus on a new probe in observational cosmology, namely 21 centimeter intensity mapping. So this is a technique that holds great promise for mapping the large-scale structure over large cosmological volumes. So in the talk, I'll discuss how we are building HIRAX as an experiment to realize this promise. And along with other stage 1 21 centimeter intensity mapping experiments, we're taking the kind of first steps in this direction, and there'll be lots of learnings, I'm sure, along the way. So to begin with the mandatory, cosmic history slide. So basically, the universe began in a hot Big Bang. Radiation dominated and matter dominated, and there's been evidence over the last 20 years that there's this mysterious component called dark energy that comes to dominate the universe at late times and causes an expansion, an accelerated expansion of the universe. So before that, structure began to form in the kind of late time universe, and as these and what we're going to focus on is probing the structure through traces of the underlying dark matter distribution. So where did all of this come from? A large part of the cosmological model has been established by CMB observations. And there have been a succession of, very successful succession of CMB experiments, culminating most recently in Planck. So these are satellite experiments. There are also a large number of ground-based CMB experiments, but mapping out these CMB anisotropies has allowed us to measure the parameters of the universe with great precision. And so if you take a power spectrum of the CMB sky, so this is the angular power spectrum, L squared CL against multipole moment L, so should be well known to most of you. We find this very rich structure of acoustic oscillations. These acoustic oscillations come from coupling between baryons and photons in the primordial plasma. The pressure of the photons resisting the gravitational infall of baryons. And this sets up a characteristic oscillations in the primordial plasma that we see in the radiation, by observing the cosmic microwave background, and we see these acoustic oscillations. And later, I'll talk about these oscillations and the imprint in the baryon distribution. So these observations have kind of led us to a concordance model, where we see that the current favored model that has 70% dark energy and about 30% matter is supported by a variety of independent observations. So this leads us to this composition of the universe where today we find that only 5% of the matter is the regular stuff that we know, and the remaining 95% is either in dark matter or in dark energy, with dark energy making up the major component. So this is great. We've measured these parameters exceptionally well, but the question is, what is this dark matter and what is this dark energy? So today I'll focus my talk on the dark energy. And as I mentioned before, we've obtained evidence for this from
initially from supernova observations that showed an accelerated expansion, but more recently, other independent probes, for example, the CMB itself, can be used to show that there's other lines of evidence for dark energy. So to answer the question, what is dark energy? Obviously, we need good theoretical models, but we also need good data to confront these models. And the key probes that have been proposed to probe dark energy, and essentially what we're looking for is a precise measurement of its equation of state. So the ratio of the pressure to the energy density, both today and at earlier times, so that we can trace or track the change from the matter-dominated epoch to the dark energy-dominated epoch. So the probes that have been proposed are, type 1 supernova, type 1a supernova, which I've mentioned already, where you measure the luminosity distance. Another probe is cosmic lensing, so basically distortions in the shape of galaxies. And there you measure both the growth factor in combination with the angular diameter distance. The third key probe is galaxy clusters, where you're basically counting the number of clusters, and that's affected by dark energy, which inhibits structure formation. And so you can distinguish between a universe filled completely with matter and a universe filled with dark energy. Here you measure the growth factor and the co-moving volume in which you're counting these clusters. Then finally, the method or technique that I'll be talking about today, Baryon acoustic oscillations. And I'll describe that in more detail in the upcoming slides. But here we're aiming to measure the angular diameter distance and the Hubble parameter. Right, and so there's a plot showing this cosmic concordance and the constraints on the dark energy density compared to the equation of state. This is a somewhat out-of-date plot, but captures this quite nicely. So this probe, Baryon acoustic oscillations, so I've just got a short movie here demonstrating how that works. It seems to be moving along, sorry about that. There we are. So what you have is, if you have initial overdensity in the universe, so we believe structure formed from these initial overdensities, you'll have an abundance of photons, baryons, and dark matter. Now, the photons are moving outwards very rapidly, and they are coupled to the baryons. So they carry the baryons out with them. But at the time of decoupling, when photons and separated from the matter, basically the free streaming length of the photons became so great that they propagated out to us today, and the baryons were left in their wake. And this sets up a characteristic scale of about 150 megaparsecs, so the size of the ring shown in this simulation. And at that distance, you'd expect to see a slight enhancement of galaxies relative to the background. So it's this slight enhancement that we are interested in terms of measuring these baryon acoustic oscillations. All right, so how do we measure these baryon acoustic oscillations? Well, galaxies trace the matter distribution. So baryonic matter that ends up in galaxies basically follows the dark matter distribution. Depending on what your tracer is, it has some bias relative to the dark matter. But these are faithful traces of the dark matter distribution. So if we can trace the dark matter distribution, then we will be able to measure the baryon acoustic oscillations signal in that distribution. So here's a plot showing that simulations, in fact, do agree with, on a large scales agree nicely with the distribution of matter in the universe. So that tells us we can use matter to trace the dark matter distribution, and then hence probe the baryon acoustic oscillation. So if we can probe the BAOs or can measure the BAOs, then that gives us a probe of dark energy, because the acoustic scale, the 150 megaparsecs that I mentioned, actually sensitive as the universe evolves in time to the angular distance and the Hubble distance are sensitive to the influence of dark energy. As I mentioned, the galaxy positions trace the acoustic scale, and the sound horizon sets this characteristic scale. So if we measure these galaxy positions, we can see ripples in the power spectrum, which are shown here in the plot on the bottom left, which also correspond to a peak in the correlation function. So that's shown here in the bottom right, and this is DR12 data released from Sloan 3, and it's shown over the redshift range from 0.2 to 0.75. So this confirms that we can indeed measure the signature, the BAO scale. And most recently, so this came out earlier this year, there have been updated results from Sloan, and in particular the EBOS results have come out, where they've used a variety of probes at different redshifts, and that's shown in this picture here, to establish the distance scale, out to beyond redshift of 2 from very low redshifts, and these are a few percent level measurements of the distance scale. And I'll speak a little bit later about the cosmological implications from these results, but the key point is to note that we can measure this BAO scale, and it's easy to predict the scale from linear theory. We can have reasonable confidence in interpreting these measurements. So thus far I've spoken about tracing the matter distribution using the optical light from galaxies, but there's actually another probe of the matter distribution, and that's neutral hydrogen. So of course, neutral hydrogen is the fuel that from which stars form, and one can imagine that by probing the neutral hydrogen distribution, one would be able to measure the underlying matter distribution, and that is indeed the case. So here's a simulation that shows both the gas and the neutral hydrogen tracing this cosmic web established by the matter distribution. Okay, so how do we trace the hydrogen? Well, we use the 21 centimeter line. So this is the spin flip transition where a hydrogen atom goes from the proton and electron spins being aligned to being anti-aligned, which is the low energy state, and that gives off a 21 centimeter photon. So we can use the 21 centimeter emission from galaxies to actually probe the matter distribution. Right. So the signal is actually the 21 centimeter signal is actually very weak. So we need to integrate for long periods of time to actually detect individual galaxies. But here's where the technique of 21 centimeter intensity mapping can assist us. What we actually interested in measuring is a very large scale, so shown here as this yellow ring. In the BAO scale is on the order of 150 megaparsecs. So we're looking for this large signal large scale signal in the matter distribution. So in fact, we don't need to resolve individual galaxies. We can actually just measure the integrated intensity from all these galaxies. And as long as we are able to resolve this 150 megaparsec scale, then we can make reasonable measurements of the BAO signature. Right, so this requires large volumes. So we need a large sky area and a large redshift range, and so the approach is to throw away spatial resolution. So we don't need, resolve individual galaxies, but that's fine as long as we get large volumes, so we can measure the BAO scale, with low cosmic variance. So once we've done this, then we can use the BAO peak and how it evolves in redshift as a standard ruler for charting the expansion history of the universe. Right, so now that sounds very promising, but there are challenges, and I'll speak of a few here. So shown here in this image is kind of looking back at what the signal, this 21 centimeter intensity signal will look like. So firstly, to note, it's at the fraction of a millikelvin, so it's quite faint, and the structure is kind of similar to the distribution of fluctuations is similar to like a map from the CMB, for example. So you're seeing these intensity fluctuations that are coming from overdensities and underdensities of neutral hydrogen, that are tracing the large-scale structure. So as I mentioned, the signal is very weak at the millikelvin or sub-millikelvin level. So we need lots of collecting area and sensitive receivers. We need a large volume to reduce cosmic variance since the BAO scale is large. So we need to measure a large sky area and cover a large redshift range. More importantly, we actually need very precise calibration. Once we collect this data, we need to be able to calibrate it. So we need a very stable instrument. And then even more challenging is the fact that not only is the signal weak, so we need lots of collecting area to build up sensitivity, but there's a very large foreground signal from galactic and extragalactic sources that's significantly larger, on the order of 1,000 to 10,000 times the amplitude of the 21 centimeter signal, and that's in intensity. So we need to characterize our instrument really well to limit any leakage of foregrounds. And I'll say a little more about this later. The good news is that the signal does exist. It's been detected not in autocorrelation, but in cross-correlation with galaxies. So shown here is the published detection in 2010. And we know that this signal exists. There have been more recent measurements in cross-correlation as well. So, this is a real signal out there, and we need to carefully design an experiment that can go out and measure the signal in autocorrelation, so that we can extract the BAO information and constrain dark energy. So, how do we go about designing such an experiment? So, the first is to maximize sensitivity on the scales of interest. So, as I mentioned, we are looking for large-scale features. So, we need to use a compact array. We are looking at a large redshift range from 0.8 to 2.5, so we can capture when dark energy comes to dominate. And we need a sufficient volume, so that gives us frequencies from 400 to 800 megahertz. We want to measure the BAO angular scale, 150 megaparsec physical scale, which corresponds to an angular scale of 1.3 to 3 degrees at these redshifts. So we need baselines if you're designing an interferometer, which is what I'm focusing on here today. Then you need a baseline lengths of something between 15 to 60 meters, minimum baselines. Since you want to measure the BAO scale along the line of sight as well, so in the radial direction, the BAO scale corresponds to something like 12 to 20 megahertz. So you need a frequency resolution across this bandwidth of at least 100 channels. But if you want to measure the high order peaks and remove foregrounds, you need many more channels than that. And finally, as I mentioned, the BAO signal level is very low. So it's at the 0.1 millikelvin level. So you need a low system temperature and you need a large collecting area, so lots of elements. So this leads us to the kind of concept that's shown in this image here of a compact array of radio kind of dishes that are operating at 400 to 800 megahertz. So this is quite different from the big upcoming radio telescopes that are being built or have been built or are being built. So for example, MeerKAT, ASCAP, the NGVLA, the SKA, etc. So they, those telescopes are designed for many scientific applications, and in particular, they usually have long baselines for resolution, and the layout is optimized to sample the UV plane so that there's better imaging. So here is shown in the top left image is the MeerKAT and the MeerKAT array in South Africa, and the baseline coverage shown in the UV plane. So this is in the kind of transform space. What you can see from the MeerKAT distribution is there's a reasonable sampling at low UV distances, so those correspond to large scales. But there's also coverage out to higher UV distances so that you can get the resolution required to detect faint AGN, etc. MeerKAT is able to trace structure on small to intermediate scales, but if you really want to detect structure on large scales, you really need to have a very compact array with all your sensitivity on the shortest baselines. So that leads us to the hydrogen intensity mapping and real-time analysis experiment, or HIRAX. Basically, it's what I described. Some of the parameters of the experiment are given in the table here. And just to add that the plan is to build HIRAX out in a scalable format where we've been funded up to 256 dishes, and we'll build it out in stages of 128 with actually an 8-element smaller version preceding that. Then out to 256, which has been funded, and we plan to have that operating by 2022. And then finally, we are in the process of raising funds to build out to 1,000 elements. And then we will operate the full array for 4 years. The dishes are stationary, but can tilt for more area, so we can achieve the 15,000 square degrees target. And we're planning to fabricate the dishes in South Africa. In terms of the back end, there's a overlap with Chime. The F engine is designed, these FPGA iSports that are built at McGill, and the correlation is done with a GPU cluster. In terms of the collaboration and funding, UKZN and the South African NRF have put in funding initially for the site infrastructure and building the Pathfinder array. And the South African Radio Astronomy Observatory is providing site power and data. There's Swiss Science Foundation funding secured to build the GPU correlator, and they're working with the group at the University of Toronto to do so. And there's McGill funding in place for the F engine, so these iSports. We've subsequently obtained NRF strategic funding to expand the Pathfinder array to the full 256 dishes, or at least to the 256 dishes that we are in the process of building now. And beyond that, we'll be looking to secure additional funding to build out to 1,024. So location is key. The image shown here on the top left is map of the cell phone coverage in South Africa, and you can see that in the Karoo region there, which is in the top left of that plot, you can see there's hardly any cell phone coverage because there's hardly any people there. And there's a series of images showing kind of the inset where the SKA and Meerkat are located and where HIRAX will be located. And in fact, it's along the road that delivers power and data to the SKA. So, we will be benefiting from that. There's an image of us, a few of us at the site. And the important point here is that in addition to there being existing infrastructure, so roads, power and data, there's very low levels of RFI. So shown here is a measurement of the RFI at the HIRAX site. And this is a very crude measurement, but at first glance, it shows that there's no significant levels of RFI that will affect the experiment. And then the other advantage I should mention is that we have access to southern skies, and there are lots of cosmological surveys in the southern hemisphere that we can do interesting cross correlations with. So just a kind of image of a few other HIRAXes. So we didn't know when we named this experiment that there's a trash metal band named of, also called HIRAX. And the resident in the Karoo, which is a DASI or rock HIRAX, is also shown here on the left. So the design plan, and I'll move quickly through this, and so I can get onto the cosmology. But basically, shown here is the schematic for the HIRAX layout, where we have 6-meter dishes, which are close packed. As I mentioned, we're building the dishes in South Africa, and we've built fiberglass and metal prototypes. There's a cloverleaf dual polarized feed, and then we carry that receives the signal, and then we carry the signal over RF fiber to the back end, where we channelize on these FPGA iSports, and then we correlate on GPU. So that's the F engine, X engine. So here are some images of some of our subsystems. The F engine and X engine are images taken from Chime, but the HIRAX system will be very similar. And also shown here are the metal and composite prototypes that have been built. And as I mentioned, we are going to be going out on tender for these dishes. So HIRAX is, I mentioned CHIME a little bit, and HIRAX is complementary with CHIME. CHIME is a cylinder experiment, whereas HIRAX is built with dishes, will be built with dishes. So there are different systematics. With the 256, we'll have a similar collecting area, and then with the 1024, we'll significantly expand our collecting area. The RFI is very good at the Kourou site. CHIME sees the whole sky each day, and that's fantastic for measuring FRBs, for example. Whereas HIRAX plans to integrate down on narrow strips, so we can, maybe target an early, quick detection on just a narrow strip where we can build up lots of sensitivity. We're observing in the southern sky, so there's optical and CMB surveys that can give us interesting cross-correlation signs, but also help us to mitigate foregrounds. And then for other scientific applications, there's more pulsars in the south because we see many more galaxies. So shown here is the HIRAX prototype array at the HartRAO Radio Observatory near Johannesburg. So we've been busy working on it to inform our design. We've been doing analysis on the data and testing our systematics. And as shown in the plot on the bottom right is the fiberglass dish that was installed, which we're also working on, and we field testing these dishes, but also field testing the radio frequency of a fiber system. And I should mention that there's complementary prototyping efforts going on at the DRAO and Green Bank by HIRAX team members based in Canada and the US. So just to show that the system works, here's some fringes from the data. Unfortunately, the environment at HartRAO being near Johannesburg is very poor, the RFI environment. So we will be shifting our efforts to the Kourou site, which is a different site from our main site, where we will be testing our qualification dishes. And as I mentioned, we're going through a tender process to select these dishes. So just briefly, our upcoming schedule, we plan to put out in the next few months the tender for the dishes, and that largely drives the schedule of the experiment. And we plan to select, probably at the latest early next year. We're also working on the RFO fiber and feeds, and we're developing a holography and drone beam calibration systems. Early next year we'll be aiming to develop the site, so put all the infrastructure in, and then on a similar time scale have the qualification dishes, which we'll work with to ensure that they satisfy our requirements. And thereafter we'll start scaling up the array on the main site, first starting with the 8-element prototype, where we plan to test out and characterize our RF system. And then we'll move on to the 128-element Pathfinder, where we'll be testing out our analysis techniques and in particular redundant calibration. So now moving on to the survey and the cosmology that we expect from the experiment. So firstly, I mentioned the redshift coverage and the survey area. So the angular coverage, and shown in the image here, is a plot that's common in this area, showing K perpendicular modes. So these are the angular scales. So L is proportional to K perpendicular, and against K parallel. And so these are the modes in the frequency direction. So the transforms of the frequency. So these K parallel modes, or you can think of it in terms of the delay as well. And what you see is that interferometers are good at probing things, scales which are in K perpendicular, which are small scales, and the dishes are better at probing large scales. So HIRAX is an interferometer experiment, and so we are restricted by on the large scales by the dish size or the minimum baseline, and on the small scales by our maximum baseline. And then the frequency coverage is basically set by the bandwidth and the number of channels. So we're planning to have 1,000 channels and the bandwidth of 400 megahertz. And just a final number that our kind of raw sensitivity per day is something like 15 microjanskis per beam. And that will give us a target of 1 microjanskis per beam for the full survey, where we'll be integrating over many strips to build up the 15,000 square degrees.
right? And this is the level required to detect the 0.1 millikelvin signal, 21 centimeter signal. So we can go ahead with these specifications and do forecasts for HIRAX, and assuming the parameters that I mentioned in the previous slide that were in the table. So shown here is the signal to noise on the left for a number of 4 HIRAX bins. And what we see is, and I'm not sure if you can see the numbers, but there's significant signal to noise in each of these pixels, ranging from 20 up to 50. And of course, we can move the signal to noise around depending on how you bin. But overall, this gives us so this is for the 1,000 element array. And then shown on the right is the precision one can measure the BAO or the power spectrum, and then the BAO signal with both the 128 element and then the 1,024, assuming this 4-year survey with 50% efficiency. So we can see that we can measure the power spectrum very precisely, and we can do this in a number of redshift bins. That allows us to convert the power spectrum measurement into a distance scale, so the BAO scale. And that's shown here. So shown in this plot are slightly older measurements of the BAO scale at lower redshifts, shown in the gray points, and then the forecast for HIRAX for the 128 and the 1024 arrays. And shown in on the right-hand side is the plot I showed earlier, which is the EBOS measurements, showing a number of measurements at different redshifts at the kind of a few percent level. So, so HIRAX with the 1024 will measure the BAOs or the distance scale across a large redshift range in a number of bins at the percent level. So that's what the forecast is. You can then turn that into cosmological constraints. So shown here are these Fisher matrix forecasts, where we've assumed a Planck 2015 prior. This is for a 4-year survey with 50% efficiency over 15,000 square degrees. And shown here are the constraints for the 128 array and the 1,000 element array. And you see that we can, we will have competitive constraints, in particular on the dark energy, and just focusing on that. Specifically, we see that the 1024 can give us tight constraints on both W naught, so the equation of state, the value today, and an evolution, the equation of state parameter WA. And the typical number that's quoted is this dark energy task force figure of merit. And so HIRAX's 1024 figure of merit is on the order of 300, and this approaches the stage 4 Galaxy class surveys, where the figure of merit is on the order of 400. And shown here on the right are the recent EBOS measurements. And what you see is the contour in the bottom right is the ellipse there shows the W naught and WA constraints, and the blue constraints are when you combine Planck with the Sloan measurements. And then when you add the supernova and other external data, you find that the error bars shrink significantly, and that actually corresponds, the gray contour there corresponds to a figure of merit, which is around 90. So that's very promising. This method, if demonstrated, can give us competitive and complementary constraints on dark energy. But that's in theory. In practice, there's many challenges that we face, and the most severe is the foreground challenge. So shown here is a selection of plots from Shaw et al. 2015, where we see that which demonstrates that in principle we can remove foregrounds, even though the foreground level is of 3 or 4 orders of magnitude larger than the 21 centimeter signal. What we can take advantage of is the smooth spectrum of the foregrounds, and we can basically filter those out. That does compromise some of the signal in the 21 centimeter, in particular in these K parallel modes. We lose modes below roughly 0.01 inverse megaparsecs.
But that are still, but the remaining scales are detected at high signal to noise and are sufficient to do the, BAO measurements and constrained dark energy. So foregrounds, are significant because of their smooth spectral dependence. And here I'm mainly referring to the intensity. Polarization is more complicated. We can hope to remove them and make a measurement of the BAO signals. So in the K parallel space, the foreground signal and the BAO signal, or 21 centimeter signal, can be separated. But that's in theory, assuming that in fact you have a perfect instrument, and the instrument obviously has many systematics associated with it. So shown here is one. And is another plot from the Shaw paper, which shows that if you have perturbations to your beam, so if you don't measure your beam sufficiently well, then that can actually start to contaminate the BAO or 21 centimeter measurements and corrupt the BAO extraction. And shown here from right to left is errors in the beam at the level of 0.1%, 1%, and 10%, and you see that by the time you get to 1% errors, you're already starting to corrupt your power spectrum measurement. So you really need to be at the 0.1% level. The equation here shows that basically, if you don't know your instrument well, so the instrument here is characterized in terms of a beam transfer matrix, and if you have perturbations in this B, then that actually gives you a leakage term. The other uncertainty is in the actual signal from the foregrounds, which gives you another leakage term. The fiducial kind of instrument description times the fiducial foreground can be filtered out, but so this is the orange kind of term that I show here. But the other leakage terms can be quite significant compared to the signal term, which I've colored in blue. So we really need excellent knowledge of the instrument to remove foregrounds. So we're planning to do that using, by having a range of calibration efforts, including beam calibration, which is going to be one of the most challenging parts of the experiment. And we're planning to do this using holography and using drones, and also to use full electromagnetic simulations to characterize. So in terms of analysis, there's, if there are non-idealities in the array, for example, in the pointing or in the positioning of the focus, John Sievers has developed a quasi-redundant calibration method, which can take these into account. But in addition to that, in advance, in anticipation of this, the upcoming dish tender, we are doing design simulations to determine the tolerances on the telescope parameters, so on the kind of mechanical assembly that will limit instrumental leakage. And so shown here is just some of the inputs from the instrument simulations pipeline that we've developed, with the Cosmology simulations pipeline taking inputs or beams from the full electromagnetic simulations. And so we're using these simulations to try to control errors in pointing or beam shape or the geometric delay that will cause non-redundancies and lead to foreground leakage. And so we're using a Fisher matrix approach to estimate these parameters. So the full parameter set of instrument, foreground, and 21 centimeter parameters. And this kind of gives you a sense of, in the power spectrum space, the kind of recovery that the simulations pipeline kind of goes through, where we include systematics and then recover the sky in the absence of these systematics to look at what impact this has on our cosmological constraints. So there's a kind of a significant effort going on within the team to try to characterize, how well we need to understand our instrument to actually make these measurements. So I'll move on now to another topic, which I guess I have probably 5 minutes left. So I'll quickly discuss these points. So I mentioned earlier that we'll be overlapping in the southern sky with a number of other surveys. These include photometric surveys like DES and LSST, and spectroscopic surveys, so a small area overlap with DESI, but Euclid and WFIRST will have fields that overlap with the HIRAX field. And on the CMB side, we will overlap with ACT and Simon's Observatory. Probably most of our area will overlap with those two observations, and in part with SVT. So HIRAX has excellent noise over cosmologically interesting scales. So shown in the plot here is in blue is the HIRAX noise curve, and we've converted it into something that can be compared to the shot noise from Galaxy surveys, and you see that albeit over the range, you know, from something like 0.02 or 3 inverse megaparsecs in K-perp to something like 1 inverse megaparsecs, even though the signal is restricted or the measurements are restricted to that range because of the interferometer scales, we actually make really precise measurements on those scales and are competitive with, you know, future kind of satellite experiments on those scales. So the fact that we have excellent signal to noise on these scales means that we can actually perform, you know, and hope to detect cross correlations with these other surveys. And these cross correlations, in addition to doing new science, are also ideal for testing systematics. So one of these applications was to photometric redshift calibration. So in the paper mentioned here in Alonso et al., we looked at cross correlation with the LSST photometric survey and how this could be used to provide photometric redshift calibration via a method called clustering redshifts. And that allows us, or that will allow the LSST to actually significantly improve their dark energy parameter constraints. So there's a specification for how well the error on the photometric redshift should be known. And that's shown here on the left, the LSST requirement and compared to the DARES requirement. And you can see that HIRAX easily meets this requirement over a large redshift range. So by cross-correlate, and the reason for this is that HIRAX has very good frequency resolution. So along the line of sight, we have a very good redshift resolution. And if you combine those constraints, you can see the improvement in the self-calibrated cosmological result compared to the calibration with 21 centimeter. And that's shown in the center plot. Right, if you have foregrounds or you remove foregrounds, then obviously the cross correlation degrades, but it's still possible to make a competitive measurement. The other application we looked at was, and this is in a paper by Jalil Ban et al. The references given there is how we can use the intensity mapping with a Galaxy survey, in particular a cosmic shear survey. And what we devised was an interesting estimator, which basically is shown in the top right plot there, and in equations on the top left, where we actually subtract the cross correlation with the between the galaxies and H1, with H1 being in the foreground, and from that we subtract the cross correlation between the galaxies and H1, with H1 being in the background. And what we've used here is that basically the first order, the H1 intensity mapping is not lensed, so that signal actually drops out. And what happens is that the main contamination, which comes from the density term, is reduced by a factor which is proportional to the bias difference, which is typically on the order of about 0.1. So we have significantly better constraints because we've reduced the variance by using this estimator. And for Euclid crossed with HIRAX, for example, we find that there's a factor of 2 improvement in this estimator, this magnification, to extract the magnification bias over a redshift range of about 1.2 to 2. So yeah, I should be finishing up now, and I think I'll finish up with another piece of work that's now involves correlation with CMB lensing. And here the challenge is that because we've removed foregrounds, the low K parallel modes actually lost, and it's these modes that are required to actually do a cross correlation with any projected field. For example, any trace of the CMB, including CMB lensing. But not all is lost because the small scale density fluctuations are coupled to these long wavelength modes. We can actually use 2 copies like shown in the figure here. 2 copies of the density field on small scales to actually reconstruct the density field on large scales. So the estimator we've developed, and that'll be coming out in an upcoming paper, is one that uses 2 copies of the 21 centimeter intensity field and 1 copy of the CMB Lensing field. And as I mentioned, this relies on modulation of the small scale signal by large scale supersample modes. This estimator actually turns out to be, oops, sorry about that. Let me get it back to the right slide. Yeah, so this estimator is quite interesting. It can allow us to provide tight constraints on the H1 bias parameters. So shown here are the 21 centimeter power spectrum constraints and then the bispectrum constraints, so the 21 kappa bispectrum constraints, and then the combined constraints. And you can see that for some of these parameter combinations, the power spectrum and bispectrum have different degeneracy directions. So this means we can independently, we can provide tight constraints on the H1 bias parameters. We can independently, oops, sorry, for some reason this is skipping ahead. We can independently constrain the growth function and clustering amplitude. And that's basically because these parameters enter in as different powers in the bispectrum and the auto spectrum. And then finally, we can improve cosmological constraints. So here you can see that the bispectrum and power spectrum give different degeneracies, and that allows us to improve our cosmological constraints. In particular, we can improve dark energy constraints. So shown here is the improvement when you add the bispectrum in orange to the auto spectrum in blue, and you get the green contour. And I've also shown here when you add the kappa constraint from the CMB, how that improves further. So we can actually reduce the errors on the dark energy parameters. So this, these cross correlations can prove to be very useful. So seeing that I think I've run over by a few minutes, I'd like to say thank you, and I look forward to the live discussions where we can discuss this in more detail and discuss other topics as well. Thank you very much.